All right, welcome to the Tutte Colloquium, and today we are happy to have Alicia Cola with us. So Alicia is assistant professor from University of Maryland, and she did obtain her PhD from Stanford in 2016, and afterwards worked as postdoc in Princeton. She worked on quantum science and physics, and if I understand correctly, she uses combinatorial and graph theory techniques to study quantum mechanics and simulations. So today she's going to talk about something that is not on the screen, so I cannot read. But welcome.
Okay, thank you. Thank you very much. I'm very glad to be here. So I'll start the screen share so we can have a look. Okay, so let's see, there we go, that's the full screen. So as Jane said, I'm actually a physicist. And so I'm very happy to have the opportunity today to talk to you all and sort of tell you how combinatorics and graph theory show up in what I do. And so let's see, so what do I do? So I make synthetic quantum systems, and I'll tell you about why I believe graph theory is really the right language for looking at my particular system. And so why would one want to make synthetic quantum systems? So basically all of the materials that you encounter in the real world arise from really just variance on a very simple set of ingredients. So you have some periodic arrangement of lattice sites, you have electrons hopping between those sites, and then they natively have Coulomb interactions. And this makes basically everything that we see in the world today, from the kinds of metals that we use for building to the wires that are in all electronics. But this also makes insulators. So it makes the insulating jacket that protects these wires. It makes our dearly beloved coffee cups. And it also gives rise to even more exotic behavior like superconductors, which can actually transmit current at no energy cost. And this is a picture of a superconductor expelling magnetic field and levitating a magnet. And so these all come from the same basic set of ingredients. And so the field of condensed matter physics is interested in really understanding how these very simple elements and different configurations and different combinations can lead to this vast variety of phenomena. And so there's several different ways, or many different ways that people go about understanding this. Sort of the most traditional experiments are to probe each material or each class of material individually. But the way that I like to think about this is really to take a step back and say that, well, in some sense, there is a notion of a generalized material that, independent of whether it's made particularly of iron or copper or nickel, what really underlies all of these is that they have a periodic arrangement of some form of lattice site, particles hopping between the sites, and particle-particle interactions. And so if we relax the requirement that the lattice site be the ionic core of some atom and that the particle moving in the lattice be an electron, then there are actually many different ways to make such a generalized material. And for each different way that you can make it, there are different ways that are easy to measure, different regimes that are easy to characterize. And so those of us that work in synthetic quantum systems, some of the keywords you may have heard for this are things like quantum simulation or quantum emulation. We like to take known building blocks and try to build up materials in different ways. And so this is what I do in my group. And so that's what I will be telling you about today. And so basically my talk will consist of 3 parts. And so in the first part of my talk, I will try to tell you about the particular hardware system that we work with and why it is that graph theory, and in particular line graphs, is the right language for thinking about systems. In the middle part of my talk, I will try to show you 2 examples where we use really the graph-like nature of the hardware that we make to get physical systems that are interesting and wouldn't otherwise be available. And then in the last part of my talk, I will tell you about the joint work that I've done largely with Peter Sarnak, trying to combine the graph theory ideas that we use to understand this system with physics methods. And we've actually been able to understand some things about periodic graphs. And sort of before I move on, I just wanted to say that, you know, I'm, as I said, a physicist by training. And so I have tried to take as much jargon as possible out of this talk, but I'm sure that I've failed in some places and that I will slip into bad habits. And so please stop me if I'm using words that aren't familiar, or if something is unclear. I have my slides on the iPad so that I can write on them if need be. Hopefully we can have a good discussion. Okay, so what do we actually do in my group? So I work in a field called superconducting circuits, or circuit QED. And basically what we do is we use the same kind of lithography techniques that people use to make electronics, and we pattern structures in superconducting thin films. And this gives us a lot of control in the microwave domain. And so we have two main building blocks that we can use to build up these synthetic devices. So the first building block is a microwave resonator, or a microwave cavity. And this is a schematic of our favorite, and we're going to use a lot of the properties of this thing. And so what you're seeing in this cartoon is how the metal layers would look like on top of our substrate. So there are these two big bars of metal on the side, and these are going to be grounded. And then the central piece we call a center pin is not connected in any way to the ground things around it. And so what this is a two-dimensional version of a coaxial cable, things that used to connect televisions, or any of you had lab courses and things like BNC cables. This is just a two-dimensional version of that kind of cylindrical waveguide. And so microwave electromagnetic modes, they propagate freely along this structure until they hit this gap region here, where there's a significant change in the impedance, and this acts like a mirror. And so it's a standing wave cavity for microwave photons, and they can be very tightly and very well confined to this structure. In practice, they look a little bit more like this. And so we fabricate them with these meanders to make them a little bit more compact and on chip. And actually the fact that we can put these meanders here is going to be very crucial for some of what I'm talking about later. But you know, this is a picture of how the device actually looks like. But you can, you know, at the heart of it, just think of these as a harmonic oscillator. The relevant degrees of freedom are conjugate, and they're charge and flux in the circuit rather than position and momentum, or position and the gradient operator. But basically this is a harmonic oscillator. We just have a lot of control over how we realize it and what we can do with it. So the other half of our building block is something that we can use to add nonlinearity to the system. And these are superconducting qubits. And so the current most common qubit is the transmon qubit. It's shown schematically here. What it is a capacitor in parallel with a Josephson junction. So for those of you for whom those are familiar words, that's fine. But again, sort of at a very high level, what you can think of this as is, instead of the harmonic oscillator we were seeing before, what the Josephson junction does is it replaces the phi squared term with cosine phi. And so this makes this an anharmonic, or a nonlinear oscillator. And that's where we can get some nonlinearity from. The other way to think about this is actually as a particle in a cosinusoidal well, and this well has different bound states that are shown here. And what the anharmonicity does is it makes the bound states unevenly spaced. And so you can address these lowest two levels alone. And in that case, you can think of this quantum bit, or sorry, this qubit as a small magnet. And this is the regime in which this is normally considered a qubit. And so in practice, what we can do is fabricate one of these qubits inside the resonator. So this is a close-up of the resonator on the previous page. And we make this extra pocket, and actually this is the circuit element that will actually produce the transmon qubit, and we can couple them together. And so we have this combination of ingredients that the coplanar waveguide resonators are easy to control and easy to pattern, and the qubits are nonlinear and act like quantum magnets. And so we can combine these two elements together. And we can think of this sort of composite system in two different ways. The more traditional sort of quantum computing paradigm is to say that the qubits are the system of interest. And in that case, actually what happens is the photons in the resonators mediate interactions between the qubits. And so you get a photon mediated spin or magnetic model. You can also think about it the other way around, is that we're interested in the photons in the resonators, and then what the qubits do is they effectively give a nonlinearity or a photon-photon interaction to the normally non-interacting electromagnetic waves. Is there a question? Okay, so then I will keep going. And so basically the theme of my research is to see what sort of interesting systems we can make when we go beyond just having one cavity and one qubit, and we start to have many different resonators in a multi-mode structure. And in particular, I like to look at periodic structures. And so for me, this is what a lattice looks like. So this is a photograph of a chip that was made in the Haug group at Princeton, maybe 5 or 10 years ago now. And so each of these squiggly lines is one of the coplanar waveguide resonators that I showed on the previous slide. And they converge at these little black dots. And so if we zoom in and take a look at what's going on at that point in the structure, we see that the center pins from 3 different cavities converge on one spot and they fan out. And in this region here, there's an extra enhanced capacitance between the center pins that allows photons confined in one resonator to jump or hop in the physics language over to one of these other guys. And so what we have here is an artificial photonic material, and the physics of this thing is governed by this Hamiltonian operator. And so this vector A, you can think of it as a complex vector specifying the amplitude and the phase of the electromagnetic field mode on each site. And so this Hamiltonian operator has 2 terms. So this first is just a multiple of the identity with the coefficient set by the resonant frequency of the cavity. And the second is describing this hopping process. And this is really just an adjacency matrix specifying which resonators are connected to which. And so the native Hamiltonian for this system is really governed by this graph adjacency matrix portion. One minor detail is that the coefficient is such that the constant function is going to be at high energy rather than at low energy. This is sort of a minor detail. But there are 2 really key aspects that make these kinds of lattices very different from, say, conventional atomic lattices that appear in materials. And so the first is that this resonator lattice site is bendable and deformable. And so here is a close-up for one of these resonators. And so what are the key properties that it has? So light that's confined in here, it propagates along the waveguide, it hits the end and it bounces back. And so the resonant frequency is really set by the arc length of this whole thing. That's how you get a standing wave condition. And the key is that the coupling is set by this junction region at the end. And because this is a waveguide, we can change how it meanders. And that means that, for example, we can make these 3 resonators, which look very different at the hardware level, But from the point of view of the microwave photons moving in this device, these three resonators can be exactly the same. And so we've made an artificial photonic material, but not at the level of imposing a periodic potential. We've really done it at the level of a graph, essentially, that we have these lattice sites which are connected to one another, and the connectivity is really what determines the physics of these guys, not exactly how they're laid out on the device or the physical proximity of the center to the center of the next resonator, for example. So these are really graph-like in this sense. The other key property that they have is that our lattice site is a one-dimensional object rather than point-like. And so if we zoom in and we look at this device, then your eye probably picked out this honeycomb lattice that I've highlighted here, but I have lied to you, because what I've done here is I've implicitly put the nodes on the coupling capacitors and the edges of the graph along the resonators. And so that's what the hardware actually looks like, but that doesn't describe how photons actually move in this material. If I want to think about how photons move in this material, I need this lattice instead. I need a vertex on every resonator, and the vertices are connected if the resonators share an endpoint. And so that means that when I look at this, there's a graph that I will call the layout graph, which describes the hardware connectivity, but the physics is determined by the line graph of that layout. And so every lattice that we make is going to be graph-like. And in fact, in particular, it's going to be realizing line graphs. And so these two properties are really key for allowing us to reach classes of lattice that aren't available in other systems. And so that's the end of my sort of introduction to the hardware. I think maybe I should pause and see if there are any questions before I move on to talking about how we actually exploit these properties to make new devices. Okay, I guess I'll keep going then. And so in the next part of my talk, as I said, what I want to show you is how we use the fact that we have really this graph-like flexibility, and in particular line graphs, to realize physical systems that we wouldn't otherwise be able to get to. And so in the first example, I will show how we use the deformability of these lattice sites to realize curvature. And in the second, I will show how we use the line graph nature of it to make something that I call a flat band. And so basically the history behind this was that we realized at some point that we had this native graph-like deformability of the resonator sites. And so we started to try to understand what did that allow us to do, because it gives a native decoupling between the realization on chip and the Hamiltonian that we weren't used to as physicists. And one thing that occurred to us is that this allows us to make curved structures. And so we could think about fullerene molecules, but also we were really intrigued by the idea of realizing negative curvature and having in the lab a system that was both quantum mechanical and curved, possibly making connections to general relativity and things like this. And so we set out to make this device. So now I want to show you how we actually do that. And so I like to think about curvature in terms of geometry and tilings, because that's sort of what I'm the most familiar with. And so this is my go-to example. This is the honeycomb lattice. And so it's a periodic arrangement of hexagons, and this is a nice crystallographic Euclidean lattice. So this is what it looks like at a single vertex, and it just continues copied with no problem. But if we go to a lattice that exists on the surface of a sphere, so there's an equivalent ish honeycomb on the surface of a sphere made from pentagons rather than hexagons. It gives you the dodecahedron, actually. And so this is what happens if you try to draw that with Euclidean pentagons. And so you see already that we have a problem that this vertex and this vertex, they should correspond to the same lattice site, but they aren't on top of each other. And so you have to stretch things out. And so this is my cartoon of a flattened soccer ball. And so I think this is a fact that you guys are probably very familiar with, that if you take something that is equidistant on the surface of a sphere and you try to flatten it, you cannot do so without changing the distances. In hyperbolic case, of course, you have the opposite problem, that instead of too much space, you have too little space and you have to start shrinking the polygons. And so this is inevitable when we go from this abstract curved space model to trying to produce a device design that has to exist on a flat 2D surface. And if you did this with, say, actual atoms and you put an atom at every vertex of this Poincare disk, then you would not get physics with equal hopping. So you would end up with something with weighted edges where sites that are close together have a much higher hopping rate or edge weight than sites here in the middle that are further apart. And so the way that we get around this is really leveraging our resonators. And so this is a cartoon of laying these resonators out on top of this soccer ball. And so it's intrinsic that the distance is not preserved, but because these are really graph-like devices, it doesn't matter that the distances are unequal. We just need to keep the terms in the Hamiltonian the same. And so if we use the same coupling capacitor at every vertex, then we can keep the hopping rate or the weight of the edges constant on all of them. And so that ensures that the Hamiltonian of this device, just in terms of the hopping term, is still given by the adjacency with all equal weights. And then the last thing that we need to fix is the on-site energies, so that we don't end up with on diagonals that are different. And we do that by changing the shape of the resonator. So if you look here in the middle, this bond distance is relatively short. And so we use a resonator that has a fairly large meander. But out here on the side where things are stretched out, we can use a resonator with a much smaller meander, keep the total arc length fixed. And that allows us to keep the Hamiltonian of the device equal to the original graph adjacency that would have existed on the surface of a sphere or in a hyperbolic plane. And so we can basically eat up the intrinsic distortion that comes from flattening this out by varying the shape of our lattice sites. And this is really the key trick. And that's what we used to actually implement a device that realizes a portion of this hyperbolic honeycomb. Okay, so this is what the device actually looks like. And so this is a 1" by 1" sapphire chip with a 200 nanometer film of niobium. And so each of these glowing lines is one of the coplanar waveguide resonators. The resolution isn't high enough for you to actually see the center pin, and so the two gaps just blur together. And so what this is the center of this hyperbolic honeycomb. So this central ring has 7 resonators, so that's these 7 sites. And then if you go out, there are more rings, such as this one and this one, that each have 7 resonators. And so you have these 7-sided cycles. And so this is the central polygon, and then 2 layers, 1, 2 of neighbors. And so this is a small piece of this hyperbolic lattice. It operates at 16 gigahertz. And in addition to the lattice itself, it has these 4 little antennae here And these allow us to actually measure this structure. We can pipe microwave photons in and out and see where the eigenmodes of the system are and try to match that to the eigenvalues and the eigenfunctions of the adjacency matrix of this graph. And this is the final result. So the experimental transmission curve is shown in blue and the theoretical in red. And so for the theory, what we've done is we've added a little bit of disorder both to the on-site energy and the edge weights, just to account for the fact that no device is perfect. So it's a fairly messy story, but what we were able to show is that we can actually control the microwave engineering of this device sufficiently well that to a good approximation, we really do realize the adjacency matrix of this graph. So we showed this in 2019 that we really could make this structure. But in addition to just making it, we also really want to understand what's going on inside. And so if this were a Euclidean lattice, then what we would do is calculate something that physicists call a band structure. So this is the band structure for the Euclidean Kagome lattice. So this is the hexagonal version of this heptagonal device that we made. And so what it essentially amounts to is using Fourier analysis to classify the eigenfunctions of this lattice. And so each of the eigenfunctions has a well-defined momentum. And so each of these surfaces is one set of the eigenvalues as a function of this momentum parameter. And the Kagome lattice has actually 3 such surfaces, one shown in orange, one shown in blue, and one shown in green. And these tell us what the single particle states are and how wave packets would behave and everything like this. And so this is the standard calculation that we would do for a Euclidean lattice. But as you all know, hyperbolic geometry is non-commutative. And so the Bloch wave techniques that we would use to derive this kind of structure don't work. And basically we are left with graph theory. And so we have to say goodbye to that beautiful plot. And instead we can fall back on graph theory results and some just finite size numerics to try to understand what's going on in this system. And so instead what we do is we take a finite sized patch of this lattice and we just compute all of the eigenvalues. And this is the list of eigenvalues that comes out. This is for the Euclidean case. And we can do the same thing for the hyperbolic one as a function of system size. And so what I've done here is that the red dots show you the eigenvalues at this very small size. Dark blue is for this one, and then we went out a few generations more. And so we can use this spectrum to, for example, compute things like the density of states, but even just looking at these eigenvalues, we see 2 very, very special things. So first of all, there's a huge set of degenerate eigenvalues here at -2. And this is very exciting from a physics point of view, because what we would like to see in these synthetic systems is that we start by having a non-interacting problem, and then we add interactions, and we would like to see really new physics come out of the interactions combining with the single particle problem. And so we're really relying on the competition between things like kinetic and motional energy and the interaction energy. And in a degenerate subspace like this, there's effectively no kinetic energy. So that as soon as you add a nonlinearity or interactions, they become the dominant energy scale, and you can have really dramatic changes in here. And so this type of behavior underlies some of the most interesting physics that condensed matter people are looking at today. So things like the fractional quantum Hall effect. And so this is very exciting. It's one of the reasons we actually made this particular lattice, but it has one other very unusual feature, which is you notice that there is a region here where there are no eigenvalues independent of system size. And so this very interesting degenerate manifolds of states is spectrally isolated or gapped. And that means that you can conceivably look at physics in that set of states without it being sort of influenced by all the rest of these more conventional ones. And so that was one of the reasons we were very excited about this particular graph and realizing it in a device. However, when you make an experimental device, there is some unavoidable disorder which tends to blur out this degenerate manifold. And so the hyperbolic lattice is actually not that favorable for realizing this. And so one of the things that we did with Peter was to try to understand why this gap is here and if there are ways that we can make it bigger. And it turns out that the reason that that gap is there is because this is a line graph. And so I just want to look at a couple examples of line graph lattices. So sorry, this is the physics name for this honeycomb. But so the line graph of the honeycomb is this guy here, which we call the Kagome lattice. We were just looking at this pair, which is the one that we actually realized in the device. But of course, you can take line graphs of many, many other things, including the tree and the square lattice. If you take the line graph of this thing here that has a vertex or a node, a vertex of degree 4, then instead of the triangles that appeared in all these other examples, you instead get this square with diagonal edges. There's actually no site in the center. And so these are the kinds of things that you can get. And we started with this example, which actually turns out to be by far the hardest of the 4 that are on this screen. And actually these two, graphene or the honeycomb and the square lattice, are a very nice starting point because we can use all of the techniques of condensed matter physics and band structure theory to compute all of the eigenvalues as a function of momentum. And so this is the band structure for the honeycomb. It has two dispersion surfaces. This is the corresponding band structure for the Kagome lattice, which is the line graph of the honeycomb. And for the square lattice, you get this sort of egg crate-like structure. And for its line graph, you get this band structure over here. And so I've drawn these with a very, very suggestive color scale to try to highlight the pattern that's going on here. So both of the line graphs have a flat band at -2 shown in orange. And then if you look, these dispersion surfaces, they look to be exact copies of the dispersion surfaces of the original underlying graph. And now this was a fact that was completely, I believe, unknown to physicists, but actually well known in graph theory. And so what Peter and I did was we really tried to link the graph theory result back to the physics and show that this mapping is in fact exact. And so basically what it turns out is that if you want to understand the physics of particles moving on a line graph, as long as it's the line graph of a regular graph, you can do it completely by understanding what happens to particles on the underlying layout graph. And so we were able to show that you can write the Hamiltonian for particles on the layout graph. If it's regular, this turns out to just be proportional to the adjacency matrix of the layout graph, and that you can connect it to the effective Hamiltonian for photons on the line graph, which in this case ends up being the adjacency matrix of the line graph. And I think this audience probably knows this whole proof, in fact, better than I do, but you can relate these two using the incidence operator, which maps from the graph to the line graph. And you can think of it as a rectangular matrix that inputs vertices and outputs the edges that are incident on that vertex. And if you multiply M and M transpose in one way, you get the Hamiltonian or the adjacency matrix on the original graph plus a multiple of the identity. And if you multiply it the other way, you get the effective Hamiltonian for photons on the line graph. And so what you end up with is this eigenvalue relation on the bottom, which was well known before in graph theory. And so what we did was connect it to these devices, which says that on a line graph, there are two types of eigenvalues. There's a flat band at -2, and everything else comes from the original graph, just shifted up. And we showed that this actually completely preserves the band structure and the dispersion relations. And it's this eigenvalue relation that really allows us to understand where the flat band is coming from and to control whether or not it's gapped. And so I like to look at a few different examples. And so what we have here is the 4 examples that I showed before, and then sketched at the bottom is the density of states of the graph and the line graph. To be fully honest, I have only sketched the support of the density of states because this pesky guy is too hard to compute. And so honeycomb is a 3 regular graph, so it has eigenvalues between -3 and 3. When you take the line graph, these move over by 1, and a flat band slots in at -2. Square lattice is very similar. And so these 2 examples, so the tree and the heptagonal honeycomb, their spectra do not reach all the way to 3 and -3. And so when you take the line graph of these guys, you get a flat band with a gap, and it's quite a bit bigger in this case. And so this was the one that we saw before, but now we can really understand that it's this complicated property here, that there was nothing below -2, there was a flat band, and then there was a gap, that really came from the least eigenvalue of the layout graph. And so if we want to realize this in a Euclidean system, we just have to find a Euclidean lattice whose least eigenvalue is not minus the degree. And so we just need a non-bipartite starting configuration. And the canonical example of this is the triangular lattice, but that's actually very hard for us to make in hardware. And so what we did with Peter was we figured out that we could make 3 regular, extremely non-bipartite graphs. And so we start from graphene. We do a process that we call subdivision by adding a new vertex to the middle of every edge. And then this is an intermediate step. So it gives us a biregular graph, which when you take the line graph of this, we end up at this structure here. And now this is a special graph because it's 3 regular, ignore the edges, but every side in the middle has 3 neighbors. That makes it very easy for us to make in hardware, but it's a 3 regular line graph. And so that means that if you compute the bands, or this is actually over here, the density of states, it has no eigenvalues below -2. And so we can use this structure as our original hardware layout. And when we do that, this is the effective photon model. I'll move that out of the way. And this is now the line graph of a line graph. And so it has a flat band at -2 and a huge gap of one hopping unit before the next states. And what Peter was able to prove is that this is the largest possible gap that you can get for starting from any 3 regular graph. Okay, and so that concludes the middle portion of my talk. And then in my last few minutes, I would just like to tell you guys about some of the rest of the work that we've been doing, where we've taken this really nice pairing of math and physics that we achieved in understanding these gapped flat band lattices, and we're actually able to sort of port some of these techniques back to understand some things about graph spectra. And so we were really motivated by 2 questions. So since we'd found this gap at -2 that was maximal and could not get any bigger, we really wanted to know whether there were other gaps, larger gaps possible at other energies, and also whether planarity imposed some fundamental constraint. So in the case of expander graphs, it makes a huge difference whether the graph is planar or not. But in terms of this line graph flat band, that turns out not to be the case, that planar graphs can realize this maximal gap at -2 just as well. And so these were the questions that we were looking at, and we were able to prove a couple of theorems. So the first is that no large 3 regular graph can have a gap larger than 2. This is my loose physicist wording of the proper theorem. And in fact, we found 2 graphs, or 2 sort of families of graphs that realize this. We conjecture that these are the only ones. And so this is the first example. And this is its band structure here. And so it has a gap between -2 and 0. And the second example that we found is this one here, which has a gap between -1 and 1. It turns out that while we found it independently, this guy was not unknown. So it was previously identified and actually proved that it was extremal, had the largest possible gap centered around 0 in this Guo and Mohar reference in 2014. And what I find also extremely remarkable is that this graph was actually also known in physics beforehand. It's hard to see in this particular embedding, but if I draw it like this, then what you can see is that this is actually a rolled up piece of honeycomb. And in physics, these are called carbon nanotubes. This one is a very small one, so it's fairly hard to realize, but larger diameter versions of this have actually seen a lot of experimental work. And what we were able to show recently is that while these 2 examples are non-planar, we can realize the same gaps in planar graphs and multigraphs. And so this -1 gap is actually the easiest, because what you can do is take a quotient with respect to an involution about this point, and that actually cuts the graph off in this way. And this terminated version of the graph is planar and cospectral. It's basically a tube-like graph. And once you terminate it, you can poke a hole in it and unpeel it. And the -2,0 case can also be terminated, although it's a little trickier. So when you take quotients of this guy, you always introduce loops. And so what we were able to find was that you can, instead of taking a quotient, you can sort of cut it and stitch in something that we call a cap. And so this particular example, it's a multigraph, but it only has multiple edges rather than loops. And again, this particular graph is planar. Now, the interesting thing about it is it's not quite cospectral with the original. It has a couple extra eigenvalues, but they occur not in this -2,0 gap. They occur in the other gap that happens at higher energy. And so the proof of this is in preparation with Peter Sarnak and Fan Wei. Let's see. So I think I have really just a few more minutes, and so I'll present our other theorem, which is that we've showed that all points between -3 and 3 can be gapped by large planar graphs. And so what that means is that if I pick any value between -3 and 3, then there exists a planar graph where that particular value falls inside a gap. So this is pretty remarkable, because what it says is that actually +3 is the only spot where you cannot put a gap. Everywhere else you can manage to do it. And the key to proving this theorem was really to combine 3 ingredients. So the first was this iteration of subdivision and line graph that Peter and I used in our previous work. The second is condensed matter band theory calculations for computing spectra. And the third was to think about lattices as abelian covers. So from what I've been told, this is really sort of the way that mathematicians would more commonly think about lattices, that you start from some small graph, you make copies, and then you sever an edge, for example, this dotted one, and connect it over. And that this is sort of a very natural way to think about translation invariance in graphs, but it was actually really not known in physics because the chemistry of this underlying graph usually doesn't make sense. If the cover is stable, it doesn't mean that this is a sensible chemical quantity. And so this is really not how physicists thought about lattices. But what's really, really nice about this particular method of thinking about lattices is that the eigenvalues of the underlying graph are the zero momentum eigenvalues of the cover. And so that means effectively you can use what's known about these small regular graphs to find likely candidates to have covers with desired properties. I think of it as almost having a periodic table of unit cells. You can look in the back of Kvetkovich, Dubin, and Sachs and find examples that have gaps in the region that you're interested in, and then try to cover them and see if those gaps remain. And so what we did was a numerical search of 1D and 2D covers of these kinds of things. And we found many, many non-planar covers, but we found a few planar covers, in particular these 4. And so what's shown in this portion of the screen is actually the gaps in the spectra of these graphs. So in red is the gaps for this one, in brown is the gaps for this one, et cetera, et cetera. And so these were found numerically, but the union of these gaps covers the entire interval -3 to 2√2, and they overlap by more than the numerical resolution. And then what Peter was able to show is that given this set, starting with these gaps, if you proceed with iterations of subdivision and line graph, you can fill in the remaining portion up here where all of these in fact have eigenvalues. And so putting those ingredients together, you can prove that you can put a gap at any place between -3 and 3, except for 3. And then finally, I'll just leave you maybe with a hopeful outlook, which is that one ongoing project that I have is to use these search and abelian cover methods to find some interesting models for error correction. And so recently, Steve Flamia and his postdoc Adrian Chapman showed that if you have a Pauli spin model that can be solved exactly by the Jordan-Wigner transformation and mapped to non-interacting particles on a lattice, that this only happens if your spin model has the anti-commutation relations of a line graph. And furthermore, the properties of the spin model are given by solving a problem on the underlying root graph just with an anti-symmetric adjacency. And so we took the code that I had developed with Peter and we modified it to take these anti-symmetric adjacencies, and we started computing all of the band structures and the densities of states, looking for examples that had favorable gap properties. And there are 2 properties that turned out to be really important. So this is an example of one of the spectra that we saw. And so one gap that's really important is the gap between the first half of the eigenvalues over here and the second half. And this is an example where that particular gap is very large. And then it turns out the other energy that's very important is if you sum the absolute value of all the eigenvalues. So this is quantity that in the graph theory literature, I believe is called the skew energy, and it amounts to summing all of these eigenvalues. And so the stability of the code depends on the difference in skew energy between the different orientations and on this single particle gap. And so we've been using my search codes to try to find examples where both of these gaps are large. And so we found, for example, this one here, where there's a very large, what we call single particle gap, and that is actually in the orientation that has the lowest skew energy. But in general, what we find is that it's very, very hard to identify models where there's a very large difference in the skew energy between the ground state and the next highest. We can find examples that have these very large single particle gaps, but very large skew energy gaps between the orientations are so far the limiting factor. And so with that, I think I will just stop and acknowledge all of the many people that were involved in this work, particularly my postdoc advisor, Andrew Hauk, and Peter Sarnak, who has been my faithful math collaborator, helping me understand the connections between all of this physics and the combinatorics, and Steve Flamia, who we've been looking at error correcting codes together, and of course, many graduate students and postdocs that have been involved in this work. Thank you. And of course, funding agencies, last but certainly not least.
Okay, thank you, Alicia, for the talk. So any questions for Alicia?
Maybe I could ask a question.
Yes.
So is there like a specific kind of material that you're looking for, or like if you find just the right graph and it has the right properties, what will you do with it?
So probably what turns out to be experimentally the easiest is to use the graph to mediate qubit-qubit interactions. Basically, the native interaction is a photon-mediated swap between the two qubits, but if you have a multi-mode structure like these graphs, then you have to include the different contributions from the different modes. And so it actually turns out that these line graph flat bands, they give you frustrated magnets. So these are very interesting, so that the wave functions are oscillatory and they have triangles everywhere. And so they tend to lead to things like glassy dynamics and things like that. And so that's, I think, the most obviously interesting place to go in the short term. You know, what we would really love to do is put, you know, interactions on the hyperbolic lattice and see what happens, but experimentally that's very hard, and we barely know what the single particle problem does. So that's a longer term dream.
Thanks.
Other questions? So I can ask one question. So I don't really know anything about physics, but I've heard some talks where, you know, this Hamiltonian, I don't know if it's defined the same, because here it looks like a matrix, but it's defined as some kind of function, exponential function in terms of temperature and also local instructions. And I guess in your talk, you also asked about, discuss the relation between the gap and energy. And I kind of feel that if the temperature goes high, then the system is become more disordered and more look like a random structure. So I just wonder,
yeah,
do you discuss anything about the gap at the other ends, like the largest eigenvalue and the second largest eigenvalue, which typically you will see a gap in random structures? I wonder if to your group ever of interest for the gap on the other ends of the spectrum.
So let's see. So there's a bunch of questions in there, so I think they're all very good. So the way that we would typically do this in physics is we kind of want to separate temperature effects, which we think of as sort of probabilistic, from sort of the general equations of motion. And so for us, the Hamiltonian, it's defined, I think, in the same way as in mathematics. It's the kinetic energy plus the potential energy. And so this particular form of the Hamiltonian is an approximate form, and it's imagining that you have a continuous potential with bound states that are in different wells. And so you can then approximate this continuum differential operator, the Hamiltonian, as the energy of the bound state and the connection between the bound states in different wells. And so you can sort of derive this in a semi-rigorous sort of perturbation theory kind of way, but it ends up being that the presence of the other wells, this is the bound state for a single isolated well, the presence of multiple wells gives you this connection term, which looks like an adjacency matrix. And this is a good approximation if the potential wells are deep. And so basically what I was trying to argue about this system is that you bypass the potential wells straight to the graph-like approximation. And so then the question is, if this is your Hamiltonian, these are your energies, then when you have temperature, then the way that we would tend to think about that is that sets whether or not your particles can jump between these different energy levels or how they fill it out. And so for us, the gap at the top is not particularly relevant. The main thing is that it's a gap to nothing. So maybe let me think maybe this is a good example. And so so the gap that we were looking at here, it's in between two places where there are states. Whereas sort of this gap here is between where there are states and where there could be states but aren't any. And so from a physics point of view, we can't really tell the difference between this scenario and this scenario. I don't know if that makes any sense. There's just, the spectrum ends there, and it doesn't make a huge difference that it ends a little earlier than it's supposed to.
But there still is the largest one, the second largest one. Like, could you see a gap there instead of the theoretical gap like 3? So
yeah, so one of the things that's a little bit tricky about this is that we have the adjacency matrix, not the graph Laplacian. And so the constant function is not an exact eigenfunction on these finite guys. And so what we find that there's nothing here because of how we cut it. But I know that people have thought about this there's a couple of papers on like phase transitions on the tree. And then the fact that there is the constant function, and then there's a gap, and then things start. And I think it's not immediately clear whether that makes a huge difference, you know, that there's only one eigenfunction there, but so it's like, it's not in the density of states because there's only one and it's a vanishing fraction of the total, but there is one guy there and it reaches everywhere. And so I think it depends on the physics that you care about, whether that one state has a dramatic effect or not. And I don't have really any good intuition for that.
Okay, thank you. Maybe we'll just leave further discussions to the after seminar virtual grad house time. So let's unmute ourselves and thank Alicia for the nice talk.